The realization of FIR filters. FIR filters are the finite impulse response filters. For realization methods, first one is direct form realization, linear phase realization, cascade realization, parallel form realization, then polyphase realization. So generally the FIR systems are the present output depends on the present input and past input does not depend on the past output. So we can say that it's a all zero filter. There is no feedback. Uh, by taking the transfer function, we have that h of z is equal to k is equal to 0 to m minus 1 bk z bar minus k. Direct form realization. For example, we can have one transfer function h of z is equal to 1 plus 1 by 4 z inverse plus z power minus 2 by 2. So generally in IAR filter, we want to realize in direct form. We have direct form 1 and direct form 2 realization. Two types of realizations are there. In direct form 1, separate delays are used for input as well as output. In direct form 2, where for the purpose of reducing the number of delays, we have common delay for both input as well as outputs. So here there is no feedback, so only zeros are there, so we can use only one direct form realization. So for that, here h of z can be denoted as y of z by x of z, then y of z is equal to x of z into 1 plus 1 by 4 z inverse z power minus 2 divided by 2. Then first, so the total number of delays here is 2, so z inverse z power minus 2, so 2 delays were added. Then x of z is multiplied by a factor 1, so it's denoted here. Then z inverse is multiplied by a constant 1 by 4, then z power minus 2 multiplied by again 1 by 2. So here one z inverse, here one z inverse, so totally z power minus 2, then added everything, you will get y of n. Similarly, for another example, h of z is equal to 1 plus 1 by 8 z inverse plus z power minus 2 by 2. So here also two delays are required. So z inverse, another z inverse. The x of z is y of z, you can write this as y of z is equal to x of z into 1 plus 1 by 8 z inverse x of z plus z power minus 2 x of z by 2. So then x of z coefficient is 1, so it's 1. Then 1 by 8 is the coefficient of z inverse x of z. So here at this point we will get z inverse into x of z. Then it's multiplied by 1 by 8, then added here. Further, the next term is z power minus 2. So here one delay, then here another delay. So totally at this junction you will have z power minus 2. This is multiplied by a factor 1 by 2. So then it's added here. Finally we got y of n. This type of realization we can call it as a direct form realization. Linear phase realization. Suppose the FIR filter satisfies the properties of symmetric condition, that is h of n is equal to h of capital N minus 1 minus n, where capital N is the number of samples. If satisfies this condition, the filter we can say that it's a symmetric. So we can have the linear phase realization. So if the symmetric means the coefficients, common coefficients can be grouped, then we can have lesser number of multiplying factors. So here if you see this transfer function, 1 plus 1 by 2 z inverse plus 3 by 4 z power minus 2 plus 1 by 2 z power minus 3 plus z power minus 4. So see here 1 by 2, here also 1 by 2. These two are common. We can make it as 1 by 2 into z inverse plus z power minus 3. Then similarly here 1 plus z power minus 4. So we can group like this. So totally the maximum delay required here is z power minus 4. So we can write in this form z inverse, z inverse, z inverse, z inverse. This is the input x of n. So totally 4 delays are there. So here at the initially the x of z, y, h of z we can write y of z by x of z. So if your y of z is equal to, we can cross multiply this, you will get x of z into this total term. So x of z plus z inverse x of z, the coefficient is 1. So here x of z, z power minus 4 into x of z. So 1, 2, 3, 4. So at this point you will get z power minus 4 into x of z. So these two terms are added, then multiplied by a factor 1. Then next you see here 1 by 2 z inverse 1 by 2 z power minus 3. So you can take these two terms. So z inverse then z power minus 3. So at this junction you will get z inverse, then here z power minus 3. Then these two are added, multiplied by a factor 1 by 2. The next term is 3 by 4 z power minus 2. Then 3 by 4. Here I am getting z power minus 2 into x of z. So finally I will get y of z. So this type of realization is a linear phase realization. So here in this type of realization, see how many maximum number of delays are required. The delays can be right in this order. So here totally 4 delays. So the first line 2 delays, second line 2 delays, like that we can write. So another example, this is another example. H of z is equal to 1 plus 1 by 2 z inverse plus 1 by 2 z power minus 2 plus z power minus 3. So here h of z we can write y of z by x of z. Then y of z is equal to x of z into this term 1 plus 1 by 2 z inverse plus 1 by 2 z power minus 2 plus z power minus 3. Then so see here, x of z coefficient is 1, z power minus 3 x of z coefficient also 1. So x of z, then z power minus 3 x of z added here, then multiplied by a factor 1. Similarly, then 1 by 2 z inverse, 1 by 2 z power minus 2. So here z inverse, here z power minus 3, then multiplied by a factor 1 by 2, then y of n. The h of z will be product of two functions. So output of the first system is given to the input of the second system. Parallel form. Now these two are connected parallelly. So input to those systems are common. So h1 of z can be denoted as y1 of z by x of z. H2 of is denoted by y2 of z by x of z. So the common input is given to both the system. The output of the first system is y1 of z, second system is y2 of z. So x of n, the delay is first z inverse, then I'll get 1 by 4 z inverse x of z, then 1 by 2 z power minus 2 x of z. So here I am getting y1 of z or that y1 of n. Similarly, the second function x of z, then 1 by 8 z inverse x of z, then 1 by 2 z power minus 2 x of z. Then I will get y2 of z. So these two y1 and y2 are added. I will get the final transfer function y of z. This type of realization is called parallel form realization. Next realization is polyphase realization. So polyphase realization means we can decompose the transfer function into some two or more smaller functions. So here in this type of polyphase realization, h of z is denoted as he of z plus h0 of z. That is, he of z denotes the even polynomials, ho denotes the odd polynomials. So here h of z, for example, we can take this transfer function h of z is equal to 5 plus z inverse plus 3 z power minus 2 plus 5 z power minus 3 plus 6 z power minus 4 plus 8 z power minus 5 plus 2 z power minus 6 plus 3 z power minus 7 plus 2 z power minus 8. So in this transfer function polynomial, we can take even powers of z separately and odd powers of z separately. So if you are taking even powers of z means 5 z power 0, the next term 3 z power minus 2, 6 z power minus 4, 2 z power minus 6, then 2 z power minus 8. The next remaining odd powers of z are z inverse, then 5 z power minus 3, then 8 z power minus 5, then 3 z power minus 7. So among these terms, you take z inverse as common, then remaining you will get 1 plus 5 z power minus 2, then 8 z power minus 4, 3 z power minus 6. Now you can have both the polynomials will have uh, same powers of z as a coefficient. So here also z power minus 2, z power minus 4, z power minus 6, z power minus 8, like that. So we can take one delay say z power minus 2, z power minus 2, z power minus 2, z power minus 2. So totally the maximum delay here required is z power minus 8. So 4 blocks are taken. Z power minus 2, Z power minus 2, Z power minus 2, Z power minus 2. So first input x of n is given here. The first term is 5. Then here 5 is added with 3 z power minus 2. So at this point I will get z power minus 2 x of n. Then multiplied by a factor 3. Then next one more z power minus 2 delay. Then I will get z power minus 4. So the coefficient of z power minus 4 is 6. 6 is multiplied here. Again z power minus 6, the coefficient is 2, multiplied here. Then z power minus 8 is, the coefficient is 2. So multiplied here. So this is the realization of the first term h e of z. Then similarly h naught of z is also realized. So see here z inverse is multiplied for the overall h naught of z. So here z inverse, then 1 plus 5 z power minus 2. So at this point I will get z power minus 2. So multiplied by a factor 5. Then 8 z power minus 4. Then 3 z power minus 6. And finally I add. So this is the y of n. So these types of realization is called polyphase realization. So